Welcome back to Davos. Still broadcasting live from the Congress Center. We had the first module this morning about setting the stage with great speakers, starting with Viola Hammer, Florian Schütz, Patrick Nicolet, and so on and so on. Now getting into the technical topics, there is a lot of ground to cover during the event. We'll be talking about new space, about cloud, about constellations, and now is the time to talk about quantum. Quantum is a very hot topic these days. We've seen a lot of investment from public organizations into quantum technologies, also coupling space. Emmanuel Macron made an announcement recently about his quantum plan for France, credited with 2 billion euros. There is a lot of talk about quantum on the attack side as well as on the defense side about satellite communications. It is a complex topic. There is a lot behind. So we invited Adrien Bécue from Airbus Cybersecurity to help us figure it out, see the big picture, understand a bit what is behind the very broad quantum term. Good morning, Adrien. I believe you are live also with us. Can you hear me okay?
Yes, I hear you. Do you hear me? Good morning.
We hear you. Good morning. Very happy to have you. You're heading the R&D and Innovation Department at Airbus Cybersecurity, expert in quantum technologies. And we are relying on you to walk us through the challenges and the potential benefits of quantum tech in terms of security for satellite communications. Adrien, please, the floor is yours, and I'll see you after with the Q&A. So please, for the participants, send your questions in the chat, and we'll relay them to Adrien after his talk.
Thanks a lot. So yeah, indeed, I'm going to talk a little bit about quantum technologies and starting with essentially quantum physics. I mean, it starts with it and the discovery of quanta and why we came to such a development of then technological bricks around quantum computing, quantum sensing, and quantum teleportation. But my focus will be on quantum teleportation applications for secure communication. So first of all, I'd like to highlight that quantum is not magic. It is a part of physics. And it is the part of physics that deals with objects at molecular, atomic, or subatomic levels. The quanta term itself comes from Max Planck from 19th century work on radiation, and then was further developed by Albert Einstein, who found this light energy element that we now call photons. And Louis de Broglie then finding out that electrons could share wave-like and particle-like properties, which the traditional physics didn't essentially admit could be shared. So essentially, why quantum physics looks a little bit like esoteric is because it somehow disturbs the rational notion we have about physics in the, let's say, human level observable elements. Then Erwin Schrödinger's wrote an important piece by introducing the theory of matter and proposing a wave function that has been then used by all quantum researchers following. Indeed, Max Born found in 1926 the property of quantum superposition, which is one of the most important properties we exploit for quantum computation, for example. And Einstein, together with Podolsky and Rose, formulated the Epr paradox, then further interpreted as quantum entanglement principle, which also challenges our minds by proposing that the state of different particles can be shared across different spaces. To start with quantum computing, it essentially is based on the exploitation of these two particularities of superposition and entanglement. In the 80s, it was proposed as the first quantum mechanical model for Turing machines by Paul Benioff. Then in the 90s, Peter Shor formulated one of the most important algorithm that enables to decrypt traditional cryptography. We'll talk further about this. In 2019, Google, AI, and NASA announced what they called quantum supremacy, somewhat claiming that they have outperformed the performance of traditional computers with quantum computers. So that's a breaking point. And now we have tremendous development around quantum computing, particularly with quantum secrets, which is the most common model that is using qubits instead of bits. And the particularity of qubits being that they can be in superposition. That means have both value of 0 and 1. Just to note what Airbus is doing there, Airbus is not developing quantum computers, but we use quantum computing to solve aerospace design and optimization problems. Then there is another important batch of techniques which we can call quantum sensing, that leverages entanglement, single photons and squeezed states to perform precise measurements. It exploits the Bose-Einstein condensate theory of 1925 that requires absolute zero temperature, where somehow microscopic quantum mechanical phenomena become apparent. Then it also relies on Heisenberg uncertainty principle that sets a fundamental limits to the accuracy with which values of physical quantities of a particle can be predicted. And Niels Bohr's observer effect, very well known for this finding that observing a quantum particle or electron would affect its state. That's particularly important for security applications, obviously. The quantum sensing is exploited either in optical sensing. We have different uses here, or non-photonic sensing. I'll discuss this further, but to give examples, Airbus uses quantum sensing and metrology for object detection, for Earth observation, telemetry and tracking, or navigation purposes. So a lot of applications in space, but also, for example, in UAV, in UAV authentication or other purposes. Then quantum teleportation is not what it seems. Again, this is not science fiction here. We are talking about the transfer of quantum information from a sender to a distant receiver. So can be interpreted rather as quantum communication, but the scientific term is quantum teleportation, and it relies on John Bell's theorem that finds out that quantum physics runs the assumptions of independence of distant events. Then we have the formulation of teleportation by Bennett et al. In '93 that found that teleporting in a known quantum state via dual physical and EPR channels was possible. So EPR channels essentially are quantum channels as we understand them. So there were different implementations. Some of the most important here mentioned Zeilinger in '97 and Povescu. So a first experimental quantum teleportation implementation. Rupert Ursin experiencing teleportation across the Danube in 2004. But let's say the record is really that of Janeway Pan research group in 2016 that were involved in this Pan cross-continental teleportation of missions satellite with Quest campaign of experiment. To talk a little bit about what Airbus is doing here is essentially using quantum teleportation in application to cryptographic key exchange. That will be quite in the focus of my speech today. Now, getting more into security matters. We have to consider quantum from a security perspective, both as a threat and in particular by the use of quantum computing to break traditional cryptography and as a solution by potential implementation of quantum cryptography to provide hopefully some secure sovereign internet in the end. So I will discuss this a bit more in details. So starting with the threat. So we found that quantum computers could outperform traditional computers. That means essentially everything we do with traditional computers with some difficulty could be made easier, and in particular, breaking keys. And we found that somewhat the most well-known algorithm and methods for encryption, namely the RSA method and the traditional symmetric cryptographic methods could be broken. So the Grover's algorithm, an important formulation that is yet quite theoretical, found that we could brute force a symmetric key into root of n attempts, and n is the key size. So at the moment, with traditional means, the only solution is to make the key size bigger, and that also has a cost. Then Peter Shor's algorithm was formulated in 1994. It brings quantum computation in power of cracking a pair of keys in a few hours. So this is even a stronger performance, and it applies in that case to asymmetric keys. So with Grover's algorithm, we reduce the resistance of symmetric cryptographies. With Shor's algorithm, we nearly annihilate the efficiency of asymmetric cryptography. Still, it requires quite strong processing power, about 100,000 times what we have at state-of-the-art with quantum computers. And we have to deal with an important challenge, which is the error rate of quantum computation that needs to be reduced 100 times. However, Airbus is considering the quantum threat as a very serious threat for the coming years. And we see implementation within 2025 quite likely. First response to quantum threat is that of the post-quantum cryptography. So just to prevent misjudgments here, post-quantum cryptography is traditional cryptography that is meant to overcome the threat of quantum. It is not a quantum technology. Still, this is quite a major technology. If we consider, for example, the assessment of these 69 post-quantum cryptography algorithm by NIST that is giving quite interesting results. I encourage you to read at the reports of 2016 and 2019 on the topic, and it's still evolving quite a lot. At this stage, we found essentially 5 candidate techniques for post-quantum cryptography that have different advantages and drawbacks. But generally, drawbacks tend to be the key size in many cases, because somehow we are struggling against the quantum computing algorithm that reduce essentially the number of attempts needed to break cryptography by brute force. Airbus is involved in one of these initiatives together with TU Munich and RISC-V in lattice implementations. So the 5 techniques, code-based, hash-based, multivariate, isogeny, and lattice are still in the run, except for the multivariate technique that apparently has been broken. And implementations are either for key exchange, that's the key exchange mechanism here, or signature. Now, quantum cryptography, which I distinguish from the post-quantum cryptography, is in fact a quantum technology, so using quantum properties. So it's radically different from post-quantum cryptography, and it actually relies on the theorem of no-go theorem from James Park, the Wisner-Brassard quantum conjugate coding theorem, and the Patti-Bronstein non-deleting theorem. The first implementation is that of Bennett and Brassard, called BB84 QKD protocol. That's the most well-known protocol, and it's very much in use specifically in quantum key distribution. It is kind of the standard, and it uses one-time pad encryption. So to provide at this stage at most everlasting security. In a simplified manner, we can consider that post-quantum cryptography provides computational security. So that means could be broken someday if quantum computers reach a certain level of capacity, while quantum key distribution potentially provides everlasting security. And that needs really to ensure that the initiation of the communication process has been successful, because somehow this is where, particularly in the authentication process, there are some remaining gaps. But there is also a way for complete message encryption that is proposed here by Subhash Kak, the 3-stage protocol that essentially aims at directly encrypting the data and not only the keys. That would provide information theoretic security, absolutely unbreakable, absolute security. Airbus at the moment is using QKD essentially to provide everlasting communication security. And I'll discuss a bit more about this later, but an interesting implementation involving space segments is these 2 approaches to quantum key distribution, where we have here on the left, the prepare and measure technique, This is essentially a technique that is relying on a secure space node. So the satellite here needs to store the key. It is interesting because it offers more flexibility. In particular, you don't need to have both Alice and Bob. I mean, the parties to the communication in line of sight. But of course, it requires this assurance that the satellite is a secure storage. Then the other technique is known as entanglement-based technique. So it really uses the entanglement principle, sends the keys, to make it simple, that to two different receivers that need to be in line of sight of the satellite. So it's more convenient with geo satellite than low Earth orbit satellites. It doesn't need to store the keys in space, so that's clearly an advantage for security. But I mean, the minus is really lower key rates because larger aperture is needed.
Adrien, if you can still hear me, I'll ask you to speed up a bit so we can leave some time for the Q&A. Thank you so much.
Sure. So with this, we can hope for a quantum internet, and that's the promise that was first formulated by Kimball in 2008. This is an extension of simply quantum communication techniques, potentially served by quantum key distribution, but that's just one of the implementations, and really the objective is to eventually encrypt the whole messages. The current state of the art is really into QKD. The advantage is that QKD can rely on fiber optics. I mean, can rely on existing infrastructure not for the key exchange, but at least for the message exchange. And that is a strong advantage when we think about the potential for deployment and for the cost of implementation. So limitations of state-of-the-art as that optical switches need to preserve quantum coherence. It doesn't work with standard switches. And classical signal amplification is not possible. So quantum repeaters will be a challenge. Airbus is involved in architecture definition for the European quantum communication infrastructure that is essentially aiming at this quantum internet. Now, the quantum communication security promise across terrestrial and space segment. I discuss here initiatives. Particularly, I open it with an overview on the Chinese experience, the longest terrestrial and longest space teleportation experiments. Then I'll talk a little bit about the European wake. That is a recent revival of the quantum communication interest among not only industry, but policymakers also, and researchers, obviously. I'll talk about quantum communication architecture, the work that's been done, particularly under European Commission's incentives. And I'll discuss some open debates, in particular between post-quantum cryptography and quantum key distribution. So the Chinese experiment, that was really an electroshock, I think, to Western arrogance towards quantum communication promise. It's an important step. There's been two steps, actually. The first implementation was this terrestrial link between Beijing and Shanghai, 2,000 kilometers, 32 different repeating nodes. And I have to state they are conventional nodes. So it is not completely quantum secure. Let's be frank, but still it's a performance, and it was also seconded by this important performance in space with the Quest initiative that related Xinjiang and Beijing, and then Beijing with Vienna, Austria. So a transcontinental communication, successful intercontinental quantum secure video call in 2016. They riposte from European actors came later. And so in 2018, 10 countries joined the Euro QCI initiative. They were then 19 in 2019, and there are now 25 countries. The interest of industry was also highlighted, particularly in this European industry white paper on European quantum security infrastructure that Airbus signed together with 24 other companies. And we see here a roadmap, if you wish, of European Union for quantum communication infrastructure definition at this stage, upcoming calls for projects aiming at a real secure quantum communication key distribution infrastructure to start with, and communication infrastructure to end with. The QCI architecture, to talk a little bit about it, includes a space segment and a terrestrial segment. Obviously, the advantage of space is to expand QCI beyond continental scale. The limitation is that it potentially needs a secure quantum space node, at least for some of the implementation. It is subject to environmental perturbation. So there's a lot of difficulties with meteorological issues, for example. The terrestrial segment doesn't have these limitations, but it has some other problems to solve, like the distance limitation. There's also an important loss, so important error rates that applies also to terrestrial segment, and there is no secure quantum repeater either.
Please, Adrien, please wrap it up. We are really running out of time.
Yeah. So just to talk a little bit about the current debate, why European institutions have been a bit slow in getting into quantum communication is particularly because of this debate between post-quantum cryptography and quantum key distribution, which from my perspective should not be a debate. Somehow we found that post-quantum cryptography and QKD have different timescales, that one is extremely mature and close to standards. The other is still a lower maturity level, but PQC gives flexibility, interoperability, low cost. It is more limited in strength and could become obsolete very, very fast, depending on progress in quantum computing. Quantum key distribution, on the other hand, provides potentially absolute or at least everlasting security, but it is costly. It's probably less available because we see that a lot of conditions need to be met so that the quantum communication works. And there is some limitation with regards to authentication security. Yeah. To finish with this, what Airbus does in quantum applies to quantum computing with solving aircraft design problems, aerodynamics. So leveraging this quantum computing capacity for complex engineering problems. Quantum sensing is in use for accurate detection and navigation in air and space. Post-quantum cryptography to secure future tactical communications and combat cloud environments, which require high availability and reliability. And quantum communication, most likely to provide European digital sovereignty and enforce privacy on future internet. That's all for me. Any questions, discussion?
Thank you, Adrien. Very complete and interesting presentation. I'll give you my takeaways, and then I'll leave the floor to Patrick with the panel. To me, if I put myself in the shoes of a commercial space operator looking at quantum technologies, I understand that you summarize it very well in your last slide, that it's not actually a battle between post-quantum cryptography and QKD, both actually complementary. This is what I learned today, and also very different in terms of time to market. So my question to you, Adrien, would be, what would be your recommendation to commercial space operators of handling this quantum question? Would you recommend, for example, implementing post-quantum cryptography on their next mission, or when? How do you see the implementation concretely for commercial space operators?
Well, indeed, for the, let's say, coming 5 years, you can consider that post-quantum cryptography will be relevant to most secure communication implementations. And in particular, if you have issues about availability, because somehow we found that the limitation of quantum communication at the moment is really about availability of assets. You cannot be sure that the key exchange will be working in the moment you need it. So whenever you have issues of ensuring safety critical implementations at the moment, I would recommend post-quantum cryptography. And even that might be limited in the sense that it doesn't address the need for time critical communication. You have this issue of key size that gets bigger, and then you need to initiate the key exchange, and it is at the moment remaining a technological challenge. But this is not better solved by QKD at the moment. So let's say if you need availability and fast implementation, or at least technologically mature deployment, then you need to go to post-quantum cryptography. Then if it's more about long-lasting secrecy, if you need to preserve state secrets, then you may think about QKD, because that is the main difference, that QKD, once the process has been well initiated, then you have an everlasting security guaranteed. So I would say in the longer term, think about QKD. In the shorter term, think about PQC. For time-sensitive applications, neither will work at the moment.
Okay. So 5 years is really the mark to have in mind to get ready to face the quantum threat. That's a bit my key takeaway. One more question from the chat about the additional costs related to implementing either post-quantum cryptography or QKD. Do you have any metrics to give the participants an order of magnitude of what they could expect to implement such solutions?
Well, I don't have figures, but so you could find on the internet the cost of the Chinese implementation. I will not give it away here. I also don't remember exactly, but it is not completely out of reach. Out of reach, I mean, of a government or a union like European Union. PQC is obviously much less costly to implement. Quantum key distribution or quantum communication requires dedicated channels. So you need to completely recreate your communication infrastructure. It needs dedicated quantum channels. It also will make use of classical channels for auxiliary functions. So that means you need both the legacy and deployed from scratch infrastructure, which spans across space and terrestrial segments if you want to reach certain distance at least.
Yeah, not a simple exercise.
Yeah,
Patrick?
maybe I have something to add in this part. Is I started to industrialize quantum cryptography from 2003, and one of the limitations of the quantum cryptography is that you need to use a dark fiber. You need to use a dedicated fiber for this quantum channel. And in the China project, they developed the infrastructure, they installed the fiber for develop this connection between these two big cities. And in Europe, we don't have right now the capacity to install this fiber, and that's the idea to discuss today about quantum and space, and it's more easy the first use case for the implementation of quantum cryptography in the space, because it's free space. We can use we don't need this infrastructure, we don't need the fiber, and the other way they are this evolution of the optical communication in space, and we can just add this in this optical communication small photon in order to generate quantum key. And that's the idea to discuss today. We discuss with the panel.
Yeah, that's the power of space, I must admit.
Let's, I suggest let's bring the panelists. I think this is perfect transition. We have a quick couple of seconds of break to get the Zoom working properly, and we are back with our panelists, including you, Adrien. So please stay on the line to join us for the quantum panel in a minute.
Thank you.